Hi all, in this lecture we will do the complete analysis of divisibility relation. Let's start with this example. So let's see this. This is a base set and divisibility relation. This relation, division relation is defined on this base set. So we already know that this division relation is symmetric, anti-symmetric, transitive and reflexive. So we already know that this is a poset. This is a poset. Why? Because all these three properties are satisfied. Reflexive, because every number divides itself. I can say that A divides A. Similarly, I can also say that this is anti-symmetric. Why this is anti-symmetric? Because if A divides B, B divides A, then it means A is equal to B. Okay. Next, this is a transitive. So these properties we already know that division relation will satisfy these properties. Okay. So all these properties are satisfied by the division relation. Reflexive, anti-symmetric and transitive. So this is a poset. Now let's make the hash diagram for this poset. So you can notice that one will divide everything. Okay. One divides everything. So one is the least element. So definitely one is the least element because one divides everything. I can say that one divides A for all A. Okay, so basically I can say that one is related to everyone. You can notice that one divides 2 and 2 comma 3, these are not comparable. So one divides 3, one divides 5 and also one divides 7. Okay, so because you can notice these are not comparable. 2 3 5 7, they are not comparable because you can notice they do not divide each other. 3 does not divide 5, 5 does not divide 3, 2 does not divide 5, 5 does not divide 2, 3 does not divide 7, 7 does not divide 3. So these are not comparable. Okay, now finally, so we have 9. So you can notice that 3 will divide 9, 3 divides 9, and finally we have 12, and I can say that 2 divides 12 and also 3 divides 12. Okay, so this is the hash diagram that we will get. Now in this hash diagram we have a least element because one divides everything. Okay, you can notice, so this is a least element. But what is the greatest element? There is no greatest element because there is no element in this poset. Okay, there is no element which is divisible by all. So I can say greatest element does not exist. And what is the maximal element? Maximal element means that element which does not divide anyone, that element which is not related to anyone. So I can say 12 is the maximal element, 9 is the maximal element, 5 is the maximal element, 7 is the maximal element. Because you can notice 7 is not related to anyone, 5 is not related to anyone, 9 is not related to anyone, 12 is not related to anyone. I can say there is no one above 7, there is no one above 5, there is no one above 9, there is no one above 12. Okay, so these are the maximal elements. Which is a minimal element? So you can notice that we have a least element, and this one is the minimal element because no one divides one, no one is related to one. One is least because one is related to everyone, and one is minimal because no one is related to one. Okay, so one is minimal and one is least. If I ask you what is the least element, least element is also one. Now think about it. Is this a lattice? We know that this is a poset because these three properties are satisfied. Now tell me, is this a lattice? Can I say this is a lattice? No, this is definitely not a lattice. So I can say, is this lattice? Okay, the answer is no. This is not a lattice. Why? Because you can clearly see that there is no LUB of 9, 12. I can say that 9 or 12 that does not exist. Okay. Similarly, I can say that 5 or 7 that does not exist. So I can say that there is no LUB of 5, 7. There is no LUB of 5, 9. There is no LUB of 7, 12. So this is not a lattice. Okay. Now, okay. So this is the complete analysis of this poset. This is a poset because this division relation is always reflexive, anti-symmetric, transitive. These three properties are definitely satisfied by the division relation. Okay. So this is the complete analysis of this poset. Let's take another example. So let me take this example. 2 3 5 7 9. Okay, division. Now let's see, is it a poset? Yes, definitely it is a poset because division relation is always reflexive, it is always anti-symmetric, and it is always transitive. These three properties are satisfied by division relation definitely. So this is definitely poset. Okay, and what about the hash diagram? The hash diagram is very simple. There is no least element, there is no element which divides everything, there is no element which is related to everything. So I can say 2 is not a least element because 2 does not divide 3. 2 3 5 7, these are not comparable. You can notice these are not comparable, but 3 will divide 9. So this is the hash diagram that we will get. Now in this hash diagram, what is the greatest element? You can clearly see that there is no greatest element. Why? Because there is no element which is divisible by all. You can notice 9 is not greatest because 2 does not divide 9. 9 is not greatest because 5 does not divide 9. 7 is not greatest because 5 does not divide 7. So there is no greatest element. And what is the least element? There is no least element also, because there is no element. Okay, to sorry, yes, there are yeah, least element is not there. Why? Because least element means element which is related to all. You can notice there is no element which is related to all. For example, this 3 is not least. Why? Because 2 is not related, this 3 is not related to 2. 2 is not least because 2 is not related to 3. So there is no element which is related to all. So I can say least element is also not there. What are the maximal elements? Maximal elements means that element which is not related to anyone. So you can notice 9 is not related to anyone else. So 9 is maximal, 2 is maximal, 5 is maximal, 7 is maximal. Remember, 3 is not maximal because 3 is related to someone else. 3 is related to 9. Okay. Now what is minimal elements? Minimal element means that element to which no one else is related. You can notice 2 is minimal because no one else is related to 2. 3 is minimal because no one else is related to 3. 5 is minimal, 7 is minimal. 9 is not minimal. This is not minimal because 3 is related to 9. Okay. So these are the points. Is this a lattice? Just check it. Is this a lattice? This is definitely not a lattice. Why? Because you can clearly see that there is no LUB of 5 or 7. So there is no LUB for these two. So I can say 5 or 7. LUB of 5 comma 7 does not exist. Similarly, 2 and 3 means GLB of 2 comma 3 also does not exist. So I can say this is not a lattice. Okay, so this is the idea. Now the important question. Okay, so okay, before I ask you this question, let's understand the definition of divisibility. Let's understand the definition of this divisibility. What is the definition of divisibility relation? Okay, so for example, remember the symbol for divisibility relation, the symbol is, this is the symbol. Okay, this symbol we call divides. This means divides. What it means? For example, if I say A, then what it means? It means A divides B. This simply means A divides B. Okay, so for example, what is this? This means 2 divides 4. This simply means 2 divides 4. And is this true or false? 2 divides 4? Yes, this is true. Okay, so 2 divides 4 is true. So I can say 2 divides 4. Can I say 4 divides 2? Answer is no. Answer is no. Okay, so 4 does not divide 2. Remember, this is the symbol. This is the symbol for divides. Okay, this means A divides B. This means A divides B. This is the symbol for divisibility relation. I am talking about relation. Okay, remember the difference. Okay, let's understand the difference between divisibility relation and division. So let's understand the difference between these two. Divisibility relation. Okay, so what is this divisibility relation and division? Let's understand the difference. Clearly you understand the difference. For example, if I ask you, remember here the symbol is, for divisibility relation, the symbol is this, and this symbol is known as divides. We call it divides. Okay, and in this division, the symbol is, for example, this is the symbol, or this slash is the symbol. Okay, so here you can notice, if I write like this, it simply means A divides B. Okay, here it means A divides B. Okay, so for example, if I ask you what is this, then this is true. If I ask you, because 2 divides 4, yes, this 2 divides 4. But remember, this will give you, so this divisibility relation will give you true or false. So this is binary, I can say. This is either true or false. This will give you true or false. Okay, so for example, 2 divides 4, true. 4 divides 2, this is false. So this divisibility relation will give you true or false. But this division, this will give you value. This will give you value. Okay, so for example, if I ask you what is 4 when divided by 2, it simply means 2. Okay, remember, this is different. For example, okay, if I write like this, then what it means, sorry, if I write like this, then what it means, it simply means what is the value when A is divided by B. Basically this value I am asking, for example, if I say that, what it means, it means the value when 4 is divided by 2, so that will be 2. So the answer is 2. So here answer will be a value. In this division, the answer will be value. And in this divisibility relation, this is the symbol for divisibility relation. This means divides, and this will give you true or false. Okay, so for example, another example you can take. For example, if I ask you what about this, okay, so this is false. I can say this is false because 8 does not divide 4. What it means? It means 8 divides 4. This means 8 divides 4, which is false. 8 divides 4. Okay, and this is definitely false. But if I ask you what is this, okay, or if I ask you what is this, okay, then it simply means the value when 8 is divided by 4, then that is simply the value. So this is the difference between divisibility relation and division. Okay, so take care about it. Now let's see the definition of divisibility relation. Okay, so you already know that if I ask you what is 0 when it is, what is the value when 0 is divided by 0, what it means value when 0 is divided by 0, when 0 is divided by 0. So what is that value when 0 is divided by 0? We already know that this is indeterminate. Okay, we already know this is indeterminate. Okay, so this is indeterminate. This value means when 0 is, okay, when 0 is divided by 0, then this value, what value you will get, that value is indeterminate. This value is indeterminate. Okay, but now remember, can I ask you, should I say 0 divides 0? Okay, basically, can I say 0 divides 0? Remember, I am not asking value here. In this divisibility relation, I am not asking value. See, here I am asking value. Like, what is the value when 0 divides 0? Okay, what is the value when 0 is divided by 0? That value is indeterminate. Remember, that value is indeterminate. So I can say this value is indeterminate. Okay, but can I say 0 divides 0? Think about it. What should I say? True or false? Okay, just think about it. What should I say? True or false? Think about it. So if you want to answer this question, then you should understand the definition of divisibility relation. So understand the definition of divisibility relation. Just understand the definition. So for example, let's assume that a comma b comma c, let's assume these are integers. Okay, so let's assume that a comma b comma q comma r, let's assume these are integers. Okay, so these are integers. Then when can I say that a divides b? When can I say this? Remember, this means what this means? This means a divides b. So when can I say that a divides b? Okay, so I can say this means a divides b. I can say a divides b if and only if a divides b if and only if b is equal to a multiplied by some integer. Okay, where q is some integer. So this is the idea. Okay, so I can say that, let's assume that a, b, q, these are integers. Then when can I say that a divides b? I can say a divides b if and only if b is equal to, okay, aq, where this q is some integer. So remember, a comma b comma q, these are integers. So for example, can I ask you, like, can I say 4 divides 8? Can I say 4 divides 8? Yes, this is true. Why this is true? Because you can clearly see 4 divides 8. Why? Because I can write 8 as, remember, a divides b. It means I can write b as aq, where q is integer. So I can write 4 divides 8. This is true. Why? Because I can write 8 as 4 multiplied by some integer. Okay, and that integer is 2. So this is the idea. So I can say that yes, 4 divides 8 is true. What about 8 divides 4? Is this true or false? This is false. Why? Because you can clearly see that 4, can I write integer? Can I put some integer here? Can I put some integer? No, okay, there does not exist. No such integer is there. No such integer. We don't have any integer such that 4 will be equal to 8 into q. Okay, there is no such integer. So this is the idea. Remember the definition of divisibility relation. This is very simple. A divides b. This means a divides b, and what it means? It means that we can write b as a multiplied by some integer. Some integer. Okay. So you can notice 8 divides 4. This is false. Why? Because you cannot write 4 as multiple of 8. Integer multiple of 8. Okay. Similarly, what about, can I say minus 4 divides 8? Can I say this? Yes, this is true. Can I say minus 4 divides 8? This is true. Why? Because I can write 8 as some integer multiple of minus 4. What is that? What is that integer? Tell me, what is that integer? That integer will be minus 2. Okay, so this is definitely an integer, you can notice. So that is the reason I can say yes, minus 4 divides 8. What about, if I ask you, what about minus 4 divides minus 4? Is this true? Yes, this is also true, because what you can say, you can write this minus 4 as integer multiple of this minus 4, that is 1. Now the same logic, okay, so like this you can apply the logic. Basically, for example, can I say that 4 divides minus 13? Is this statement true or false? This statement is false. Why? Because this minus 13 you can never write as 4 multiplied by some integer. No such integer. We have no such integer. There is no integer such that minus 13 is equal to 4 multiplied by it. Okay, so there is no such integer. So this is the idea. Now think about it. Can I say 0 divides 0? Yes, this is true. Why 0 divides 0? Because you can write 0 as integer multiple of 0. Okay, so we need some integer. Remember, just remember the definition. Apply the definition of divisibility relation. In the definition, basically what we are saying that A divides B. Basically what we are saying A divides B if and only if B is some integer multiple of A. B is some integer multiple of A. B is some integer multiple of A. Some integer multiple of A. Okay, some integer multiple of A means I can say A divides B if and only if there exists integer q, such that B is in this integer multiplication of A. Okay, so there exists some integer such that B is equal to QA. So this is the idea. Now you can apply this idea here. Can I say 0 divides 0? Yes, this is true. Why? Because I can write 0 as integer multiple of some integer. Can you give me some integer? Yes, you can give me some integer. Just give me some integer. I only want there exist. Remember? So I can say 0 divides 0. Okay, why? Because 0 divides 0. This is true. Why? Because there exists integer. Remember, there exists integer. Okay, there exists an integer q, and this q you can take as 3. There exists integer q, you can take it as 3. We only want there exist. Okay, we only want some integer. Such that this 0 is equal to this multiple of. Okay, so I can say 0 divides 0. Yes, this is true. Now remember the difference. 0 divides 0, that is true, because this is a relation. Remember, this is divisibility relation. Okay, so because this is divisibility relation, so the answer is true. But if I ask you what is the value is indeterminate. Okay, so this value, if I ask you like what will be the value, if I ask you what will be the value, this value is indeterminate. Okay, so this value is indeterminate. But remember, yes, 0 divides 0, but this value is indeterminate. For example, I can say 4 divides 8. This is true. And similarly, if I ask you what is the value, when 8 is divided by 4, this is the value. The value is 2. Okay, so this is the idea. So 0 divides 0, this is true, because this divides, this is divides, this is your divides, and this is a divisibility relation. So the answer will be true or false. And here we are. Okay, when I do this, then this basically means I am asking you value. If I ask you what is the value, then the answer is indeterminate. But if I ask you does 0 divide 0? Yes, 0 divide 0, because you can apply the definition of divisibility relation. Just apply this definition. A divides B if and only if there exists some integer such that B is equal to QA. So this is the idea. Okay, so can I say 0 divides 0, true or false? And the answer is true. 0 divides 0, that is true. Okay, so if this concept is clear, then so let's do the analysis of this. And okay, set of natural number, and this is the divisibility relation. So this is your divisibility relation. This is the divisibility relation. Okay, so this is set of natural number. Set of natural number means 1 2 3 4 and so on. This is the set of natural number. So now tell me in this, so first of all, what will be the hash diagram? Just try. Remember, this is your infinite set. So your base set is infinite, so your hash diagram will have infinite number of elements. Okay, so but if you want to create the hash diagram, then it will be looking something like this. Remember, 1 is the least element, because 1 will divide everything. So this 1 will be the least element, because 1 divides everything. 1 divides, okay, A for all A which are natural number. 1 divides everything, so I can say 1 is the least element. Okay, so you can clearly see that 1 divides 2, 1 divides 3. Remember, on this level all these elements will be there. Okay, for example, all the prime numbers will be there. All the prime numbers will be there. So like this, you can just make all the prime numbers will be there like this, and so on. All the prime numbers will be there, because these are not comparable. All these things are not comparable. You can notice 2 comma 7, these are not comparable because 2 does not divide 7, 7 does not divide 2. You can notice 5 comma 17, these are not comparable. Okay, so this is the idea. And now you can notice 2 divides 4, and so similarly, okay, so 2 divides 4, then where will be 6? So I can say 6 will be here because 2 comma 6 that divides 6. Okay, so where will be 8? So I can say 8 will be here because 4 divides 8. So like this, okay, so like this you can create. Where will be 9? Okay, so 9 will be here because 3 divides 9. Where will be 10? 10 will be here, and 5 divides 10, and also 2 divides 10. Okay, so like this you can create the like this you can create the hash diagram. So the hash diagram will be infinite. Okay, so this is just to give you idea. So all the prime numbers are here. You can notice these are all the prime numbers. Okay, so this is the idea. This is the idea of hash diagram. Now what is the greatest element if I ask you? So the least element, you know. Okay, so in this set of natural number comma divides, in this you know the least element. What is the least element? Least element is 1. Why? Because you can notice that 1 will divide everything. I can say that 1 divides a for all a in the base set. For every number, for every natural number, I can say 1 divides everything. So I can say 1 is related to every number. Okay, so this is the least element. What is the greatest element? Is there any natural number which is divisible by all? Is there any natural number which is divisible by every natural number? No, so does not exist. There is no natural number which is divisible by all the natural numbers. So greatest element does not exist. Okay, and the least element is 1. So this is the idea. Okay, now let's see this another question. Set of whole numbers comma divide. Okay, so this is set of whole numbers, means set of non-negative integers. So this is 0, 1, 2, 3, 4, and so on. First you check, is this a poset? Okay, so first you check, is this a poset? Is this reflexive? So can I say this is reflexive? Can I say that every element here, can I say in this is your base set? So this is the base set. Can I say in this base set every element divides itself? Can I say? Yes, this is reflexive because you can notice for all a in our base set, I can say a divides a. Can I? Okay, so because you can notice 1 divides 1, this is true. Okay, 2 divides 2, this is true. Can I say 0 divides 0? We have already seen, yes, this is correct. 0 divides 0 because this is divisibility relation. I am not asking you value. Remember, here I am not asking you value. I am asking you 0 divides 0 or not. Okay, so true or false? Yes, this is true. 0 divides 0. Okay, because what you can say, I can write 0 as integer multiple of 0. Okay, so I can say just 0 divides 0. So reflexive property is satisfied. So this is the reason I told you that this division relation, remember this divisibility relation, okay, this divisibility relation is definitely reflexive. This is always reflexive. Okay, this is always reflexive, this is always antisymmetric, and this is transitive. Okay, so this is always transitive. Now let me tell you one thing here about this antisymmetric. Let me tell you about this here. See, if you do this, for example, set of integers comma divides. Okay, set of integers comma divides. Now this is not antisymmetric. Now actually this is not antisymmetric. Here this is not antisymmetric because what is the reason? The reason is because 1 divides minus 1, also minus 1 divides 1. For example, 2 divides minus 2, also minus 2 divides 2. So this is the reason. Okay, this is the reason I can say here this is not antisymmetric. So when I am saying, for example, divisibility relation is reflexive, antisymmetric, transitive. Okay, when you have, okay, for when base set has no negative integer. Okay, so for I can say for whole numbers. Okay, what I can say? I can say for whole numbers. For whole numbers means for non-negative integers, I can say this. Okay, so this is the idea. Remember, if you have set of integers comma divides, then in this case this is not antisymmetric because 1 divides minus 1 divides 1. So I can say this is not antisymmetric here. In this situation, this is not antisymmetric. So take care. Okay, so this type of base set, if it is given, then you should take care. Now let's see. So this is the set of whole numbers. So yes, this is reflexive. For set of whole numbers, this is antisymmetric also, and this is transitive also. Okay, so this is the idea. Now, okay, so here, so in this w comma divides, what is the least element? The least element means element which divides everything. Least element is 1 because 1 will divide everything. Okay, 1 divides everything. So this is the idea. So 1 divides everything. What is the greatest element? What is the element which is divisible by all? Which is divisible by all? Is there any greatest element? This is your base set 0, 1, 2, 3, 4 and so on. This is the base set. So do we have greatest element? Yes, greatest element is 0 because everything will divide 0. A divides 0 for all A. Okay, every element will divide 0. For example, 0 divides 0. For example, 1 divides 0. 2 divides 0. Every whole number, every non-negative integer will divide 0. So here we have greatest element 0 and the least element is 1. Okay, so these are some variations in the divisibility relation. I hope all these variations are clear. Okay, now let's move on. In the next video we will study a very special type of base set. See, remember, okay, I'm giving you different base set. For example, okay, the relation is divisibility, relation is same, but I can give you different type of base set. This type of, okay, different base set I can give you. For example, 1, 2, 3, okay, and so on. So here you can clearly see that this is how I can give you different base set. Okay, so can I say, okay, can it become symmetric? For example, if I give you this base set, just consider this base set 1, okay, just consider this base set, then in this situation this is reflexive also, this is symmetric also, and this is anti-symmetric also, and this is transitive also, this is transitive also. Okay, so remember, it will depend on the base set. So okay, so take care about the base sets. The relation is divides, the relation is divisibility, there is no problem here. The relation is divisibility relation, but you should take care about the base set. What is the base set? Use, okay, it should depend on that. For example, if I give you base set as 2, 3, okay, then in this case what properties are satisfied? You can clearly see reflexive property is satisfied. Here it is also symmetric, this is also symmetric because 2 divides 2, 3 divides 3. So actually if you notice, what is this relation? This relation is actually 2 divides 2, 3 divides 3. This is your relation. You can clearly see this is reflexive, you can clearly see this is symmetric, this is also anti-symmetric, and this is also transitive. So take care about the base set. Okay, so the relation is same, the relation is divisibility, but you should take care about the base set. What is the base set? For example, if I give you this base set 1, 2, 3, if I give you this base set, now reflexive, and now, okay, of course reflexive is fine, anti-symmetric is fine, but okay, but now this is not symmetric. But now this is not symmetric because you can notice 1 divides 2, also 2 divides 1. This is not symmetric. Why this is not symmetric? Because 1 divides 2, okay, but 2 does not divide 1. Okay, so I can say that this is not symmetric. Okay, yes, it is transitive. So this is the idea. Okay, so these are some variations on the divisibility relation. You should take care about the base set. So definitely this base set you should take care, because I told you, for example, if you have this one, okay, this one, if you notice, this is symmetric, this is not this is not anti-symmetric, this is not symmetric. So you can clearly see this is not symmetric, and you can also clearly see this is not anti-symmetric. Okay, so this one, set of integers comma divides, this is not symmetric. Why this is not symmetric? This is not symmetric because you can notice 2 divides 4, but 4 does not divide 2. This is not anti-symmetric because 1 divides -1 and -1 divides 1. Okay, so here you can notice, for set of integers comma divides, this is not symmetric, this is not anti-symmetric. But you can notice this is anti-symmetric, reflexive, transitive, so this is a poset. And similarly these are also poset. Okay, this one and this one, these are also poset. Okay, so this one and this one, these are also poset. Okay, so you should take care about the base set, the base set. Okay, so take care about it. Now in the next video, what we will do, we will study a very special type of base set. Okay, with the divisibility relation, the relation will be same, divisibility, but the base set is very special, and the base set is denoted by dn. What is that? That is set of all divisors of n, set of all divisors of n. So this is a very special type of, this will be created, this will create a lattice, this will create a lattice. Okay, and this is a very special type of lattice. So we need to do the complete analysis of this. Okay, so in the next video we will do the complete analysis of this lattice. We will see that this is a lattice, we will see, okay, why this is a lattice. I will tell you why this is a lattice, but the complete analysis we will study in the next lecture.